talking too low. So
Okay.
I was telling some amazing stories about how Ali was great. If you for those online, but came and did his PhD, graduated a few years ago, and went to AMD Xilinx Research, and kind of the rest is almost history now. So he's back here. It's really great to have him back in San Diego. He's living in Colorado now. But it's always good to have you back, Ali, and he'll come and talk to us about some of the great research that he's been doing at Xilinx AMD Xilinx Research Lab. So without further ado, Ali, please.
Excellent. Thank you very much, Ryan. So you know my name now, and I'm still at Triton. So um, today I'm going to talk about Open Computing Project and the new data types that are proposed for AI. All right. Good. Hopefully it's better now. And my main goal here is to excite you for the potential projects that you can pick up. And the work I'm presenting here, there are a lot of people involved. I did a tiny portion of this work. But hopefully you, based on your focus in research and your studies, you find one of these parts interesting, and hopefully you can collaborate with us. If not, there are a ton of other people out there that they love you to collaborate with them, like NVIDIA, Intel, and other people that are not as good as AMD. So let's just start with what is important. Uh, Technical difficulties. There you go, hopefully. Okay, money. You probably heard in the news that the cost of, excellent, thank you. The cost of AI is increasing. It's not just money, it's power, it's a lot of carbon footprint, um, and everybody wants to reduce the cost. We want to reduce the cost in order to bring those applications to consumer devices. Like we want you to use your laptop or hopefully your cell phone to run some of those applications. But currently the cost is high, and the cost is, it includes a bunch of stuff. It's the cost of hiring people who are experts who design these models for you. It's the cost of collecting those data sets. And another cost is the computational cost is very much associated with the size of these models. Since 2018, you can see we are on a almost linear path of growth for the size of these models. They're just growing by a lot. You heard ChatGPT has more than 175 billion parameters. There are other models out there that are not open source, so we don't know how big they are. There are models that are, discussed, but the way they are being trained or the devices that are being trained on are not disclosed. So the size of these models are going up, and one obvious solution is to do something about that. You probably heard about compression methods, reducing the number of parameters by pruning, or quantization. And quantization means using another data type to encode your parameters. And since 2020, which is very end of the slide on the left, so like here, you can see a lot of papers are being published that they are proposing new data types. Smaller number of bits encoded into integer, floating point formats, being scalars, and etc. So I'm going to talk about a few of these solutions, give you the big picture, where are they coming from, why we are looking into them, and how to choose the best data type. In order to show you what's going on, I select an absurdly simple example to talk about neural networks. I have a model here. It has a shape, like a conic shape. You can think of models like VGG, ResNets, encoder, decoders, transformers. This is a shape. It has a shape. For that to represent that shape, I have a few parameters. I have a center and I have a radius. And my inputs are just 4 dots on the unit circle, A, B, E, and D. And for now, I like to just take one dot as an output, which is A. It's pretty easy. I just need to put my shape very close to that A, the center, with whatever radius. It should be small, not big enough, not big in order to not cover the other dots. Very simple solution. If I want to have another output, like A and B, I can adjust my radius a little bigger, still 2 parameters. I just need to be careful to not cover D and E. And same for 3 dots. And I come to an output that I like to select 2 dots on the opposite side of that axis. Now I have this problem that I cannot just dissect those to the circle. I need another model, another shape, another solution. It can be an ellipse. It's just R1, R2, and the center. So based on my task, the model gonna change. The number of parameters gonna change. You can think of classifying MNIST. 4, 3 layers, easy, you get the best results. You go to CFAR10, you need something bigger, more parameters. You go to ImageNet, you probably need a little bit of residual connections and etc. You go to LLMs, you have these heads and self-attention, a number of them, encoder, decoder, they just get very complex. So this is a cartoon of the complexity of the model. And the whole point is to tell you that the number of parameters, the shape of the model, totally depends on what you're going to do on your task. The other thing here is, how do you represent those parameters? Like the center, R1 and R2, how do you encode them? FP32 is very familiar to pretty much every, at least CSE, hopefully CSE students. Your laptop, your GPU, your daily devices that you use to run your tasks, they support FP32. You can encode 0.5, 1.5, 0, and 0 with FP32. But it's too large, it's too many bits, right? For here, it's fine. I mean, like 4 parameters, it's not a big deal. But when you go to 175 billion parameters, when you want to run them over and over in many epochs, you want to go backward fast, you have to do a lot of multiplication, accumulation, etc. You don't want to use a lot of number of bits. Data movement, also computing very wide data types is very costly. Maybe applying a very simple filter on your cell phone, probably gonna drain your battery by a few percentages. You don't want to do that, right? You want to reduce the size of your processor. You want to reduce the size of the memory. You want to reduce the power usage. So you have to be creative. For example, you can go to FP4, reduce the size of the number of bits used to encode your parameters, and come up with a new data type. It's not important. You don't need to understand how the calculation works, but you have 1 bit for sine. It's the red one. 2 bits for exponents. I'm going to scale it, and then 1 bit for precision to say, okay, what do I have? What's the step size here? FP4 going to cover that. But if I move this shape from the center to here, my center going to be in somewhere else, -32, -16. I don't have the dynamic range in FP4. I need more bits to encode my parameters. I can go back to FP32. I can go to something larger, I don't know, FP16, but maybe I can see some patterns here and say, okay, maybe I can do something smart. Maybe I can multiply those numbers by a scale, and I can share that scale between a few of my parameters in a layer, in a tensor, in a channel, and etc., to save up some bits. It's good because I have, if I want to save these parameters, I need smaller memory, and if I'm smart with my scalar, if it's just power of 2, I can do my scaling by just shifting. So the data type of the scaling is important. the size of the scale is important, but it comes with its own challenges because now it's weird. It's like I have 2 4 bits and a 5 bit over there. Memory alignment is a little weird here. If I have multiple of these numbers, how do I move them? How do I store these scalars in the memory? So these solutions, these challenges here are not limited to one section of the pipeline. They're like full stack problems from coming up with solutions to reduce the size of these parameters in PyTorch or TensorFlow, how to export them to some format like Onyx, what your compiler going to do with them, the optimization for data movement, and etc. What kind of kernels you're going to put on the device, what device you're going to use, and also the big question here is which data type is good, right? If you make a device, if you seal the deal on your chip and you ship it out, maybe someone else gonna come up with another data type that which you don't support, and nobody gonna buy your device. So generality to support a bunch of data types that are useful is also important. And to just add one more dimension to the complexity, the shape didn't move, but over there the center is -32 and -4. So I just changed the center to something else, but the shape didn't move here. In many models, you have the problem with dynamic range, right? So over there, the FP4 didn't cut it. It didn't have enough dynamic range. I had to step up, add more bits into my encoding for the values, go to FP6. If you follow up the papers regarding compressing these models, one of the issues for language models, when they get very large, when they go to 100, tens of billions of parameters, at the you start having outliers in your activations. So imagine you have a few parameters, and then one of them is very large. So you need that dynamic range. You cannot just use a very narrow data type. You have to be creative. These data types are not imaginary. They're out there. People are taking them seriously. This is another slide is just intended to catch your attention of recent very large models for LLM. Most of them, well, I want to say most of them, but some of them may not be publicly available. But the one on Hugging Face, they're also available in FP6 and bfloat16, right? You can just download them as FP16, bfloat16, and if you have a GPU that supports FP16, you end up with half the size of FP32. And pretty much no decrease or no change in the quality of the model. Your accuracy doesn't drop when you go from FP32 to FP16. It's very, very rare. So it tells you something. It's like FP32 is an overkill for most of these models. FP16 is fine. There are other papers that they discuss even narrower data types, FP8, int8, int4. But to get to those data types, you have to do a little more. You have to do some post-training quantization. You have to like adjust your weights when you quantize them to int8. You cannot just cast them to FP16. You probably have to do some fine-tuning, running a few epochs or using like knowledge distillation techniques to get to int4. They're not easy to get, but it's possible. There are also other proposals online that they come up with even more complex data types, like hierarchical quantization. Like Hulora is a paper, the llama.cpp. It's getting a lot of attention. It's actually running llama in C++, so PyTorch involved, and they have like super block and block scale data types. These models are available if you want to download it on Hugging Face. The block, BLOK, is the person who quantized these models to these data types. And if you download and use their data types, you can donate into their Patreon account. And that's that guy's job. That's all he does. He does quantize them and puts them there for whoever wants to use them. So there are some patterns here. Yes. Yes. Okay, I'm going to repeat your question for the online folks. The question is, if you go from a wider data type to a narrower one like FP32 to int4, do you get the same performance? Fair? Pre-training in int4. Yeah, so yes and no, and I don't know. Yeah. Yes, for many applications, you can quantize to int4 and get the same performance with pre-training, training with quantized formats, or trained with FP32 and then quantize. No for other ones. And the I don't know part are the models that are not publicly available. And why is that? Because I'm going to show you some tables that they show the performance, the accuracy for quantized models. And you can see in each row that you have some sort of indication of quality, perplexity, accuracy, whatever. There is a data set here. It's quantized for that data set. If you increase the size of the model, like if you have a model with 125 million parameters, like OPT 125M, right? You quantize it for tweet classification. Is it tweet happy tweet or it's a sad tweet, right? 125 million parameters is an overkill for it. If you go to OPT 175 billion with the same task, I can tell you that you can just delete a couple of those, more than a couple of those layers, and still get the good results, right? So it depends on what you want to do. If your task is complex, if you want to have an interaction with one of those LLMs, and if you want to use the same model to as a co-pilot for C++ and Python, and maybe do some search for you online and a bunch of other stuff, it's very hard to quantize it and it's still having the same quality. But if you say, no, I just want to do C++ with this guy, like Copilot for C++ code, you can quantize it much more aggressively. Did I answer your question? Okay, good. All right. So the possible data types right here, they usually have some, like, you have a value, that weight, right? It's just one of your parameters. In red up there, here, and you have so many bits per that value, right? If you reduce the number of bits there, you have to kind of look at the model to see what's the dynamic range there, right? What's the similarity? It's very hard to find any like expression of the distribution in those tensors. Like it's very dependent on what is your input, what are your weights, and etc. So you have to be kind of like think about it in a general way that I'm going to cover most of the scenarios. So per weight, you have a number of bits. If you reduce the number of bits, at some point, you cannot cover the dynamic range. You need another scalar. So that scalar can be per tensor, right? Can be per channel, like Professor Sub, Brian Sub is online. His student, Jinji Zhang, has this GPFQ paper that has a per tensor scalar for to quantize these weights to int3 and int4. Per row, GPTQ, hopefully you heard that name. It's a very famous paper out there that does per row scalar. You can go per block, so it's smaller than a row or a column. You can stack those together and make a super block, like that's QLoRa that I just mentioned previously. But you have to be careful because, for example, if you do per row scalar, right, and then at some point you transpose your matrix, right, that per row now is a per column. It's very hard to manage the bookkeeping, sorry, in the hardware. So you probably have to go per channel or per tile that in a transpose, your scalar orientation that, preserve its characteristics. So depending on your application, what you want to do, you can choose between these guys. And as I mentioned before, you can also do hierarchical. So here, I'm just showing an example. I have int4, 1 bit for sign, 3 bits for um, um, not sign per value. And then I can group those int4s in a block. Here my block is 4. Imagine here you have 4 of these int4s. And I can have a scalar per that block. And I can group those blocks into something bigger and call it super block and have yet another scalar. So it has a couple of benefits. If you don't do the per block, per super block scalar, the size of your scalar per block going to be larger, or the data type going to be challenging. What is challenging? Like, for example, if I manage to have my per block scalar as power of 2, I can scale my results at the end just by shifting it left and right? And then at the end, I say, okay, for the super block, I'm going to use some narrow FP format, right? So that's one benefit. If I get rid of the super block scalar, maybe my per block scalar going to be larger, or the data format going to be some sort of FP floating point narrower, like not 32 hopefully, but maybe FP16. And then the computation with FP16 in those kernels is costly. It's costly and also it's slower. You know, you need more calculations or latency, throughput. It's going to affect everything. So that's why these solutions are popping up here and there. And also the orientation. I have listed a few questions there. What's the data type of your values? Here is int4. It can be anything else. What's the block size, the orientation, and etc. And the question is, which one is good? Which one should we choose? Yes. Yes. Good question. So the question is, do you have an offset? If you can read like some 0 point or minimum or something like that. Yes. If you go and take a look at the K-quant, sorry, my K-quant, which was the hierarchical data type available on Hugging Face. For smaller data types, for like int2, they do maintain a minimum. And that minimum per super block is FP32. What does that mean? At the end of the calculation, you have to do some FP32 addition. It's costly. But yes, sometimes you have to do that. And sometimes you do asymmetric quantization. You have to keep track of your 0 and stuff like that. It depends on your application first, and also the hardware support, right? Yes, they do keep track of minimum or 0 or some bias, as you said. All right, so the question is, which one is better? To be honest with you, we don't have a silver bullet. We don't have a solution for all the problems. But we think we have a good solution for now, which is the OCP. I'm going to show you in a moment. The reason is it has a high dependency on your model input and outputs. I cannot repeat it enough. The model, the input, the output, the task is very, very important. Right here, for one layer in the middle of this cartoonish example, if you quantize your activations, you end up with some quantization error, that delta AI. That's the difference between the original values and the quantized values that are coming into your layer. If you quantize your weights, right, you add something, and then it's going to be that delta AI plus 1. That's your output. So when you quantize, your input going to change, your output going to change. And the relation between these input and outputs to your final quality metric, delta P, that can be accuracy, perplexity, or etc. It's very hard to calculate. for example, a lot of people say if you want to find out how sensitive the p-value is to each weight, you need to calculate the Hessian value, the Hessian matrix, right? Hopefully you are familiar with the Hessian matrix. It's the second order derivation, and it's very, very costly to calculate. Nobody does it. If some papers, they try to use it, and in those papers, in those works, you just calculate the diagonal of that matrix. And in order to calculate that, you don't calculate the actual numbers. You estimate the eigenvalues, the largest eigenvalues that are going to represent, give you some feeling of sensitivity. That's all you get. You don't get per value accurate information. In other ways, like it has connections to adversarial attacks. Like if you read those papers, they say if you change your input for attacking, right now we are changing the input by quantization. The way to measure the effect, you can calculate the norm of the Jacobian, the norm of the Jacobian of these matrices. It's not cheap to calculate. It's cheaper than Hessian. You can also look at the output of your nonlinear function. You can see how many numbers flipped between 0 and non-zero. That's also another metric to look at. But these are not cheap. So, and also there are solutions per model, per input. They are not like you look at this OPT 125, and then you can take that solution and apply it to GPT 3.5. It's not going to work, most probably. So it's a very hard problem to tackle. There are a lot of fruits there, low-hanging fruits or not low-hanging fruits. I heavily encourage you to look into it. Try to study the problem, come up with some solutions that are a little bit general. They can cover multiple different scenarios, and we love to work with you. If you don't like AMD, there are a ton of other companies out there that they love to have solutions for this, guys. Or you can be a lone warrior on Hugging Face and have your own Patreon account. I will donate to you. Okay, so the Open Computing Project said, let's for now, at least, come up with a solution that is general enough and it's going to satisfy a lot of criteria. It's not the final solution, but it has the support of these many companies: Qualcomm, Meta, NVIDIA, Intel, ARM, Microsoft, and the best, AMD, behind it. The specifications are on opencompute.org. We have a white paper to explain how to use these data types. And Microsoft also published a library based on PyTorch. So you can play around with them. You can quantize models with these data types, apply some algorithms, fine-tuning, etc., to see how it works. But basically, we say, let's have a block of numbers, a few numbers, k elements, right? Each parameter has d bits. And we're going to have a scale that's going to be shared between them with w bits, right? And for version 1, we came up with these data types. They are pretty much three, you can separate them in three categories: FP8, MXFP8, meaning each parameter, the D is like 8 bits. The encoding can be different, like E5M2 means 5-bit for the scalar, for the exponent, sorry, and 2 bits for mantissa. You can change it to E4M3, right? And each one of them has its own benefit. It's a trade-off between the dynamic range and the precision, right? So if you have a large dynamic range, E5M2 is better than E4M3. If you care about the precision, maybe you should switch to larger number of mantissa. Int8 has M7 with 1 bit of sign, 8-bit, but no exponent. It's just integer. And MXFP6, it also has 2 variations, and the smallest one is MXFP4. As we speak right now, people are talking about MXInt4. So MXInt4 is another option here that may come in the next version. The scale data type here for all of them for now is E8 M0 power of 2. So it's just power of 2 exponents. It's good because you can scale it by shifting left and right. That's it, it's easy. The number of elements in each block is 32. It can be also a multiplier of 32. So you can put these blocks next to each other, go to a row, go to a tile, channel, or the whole tensor. You can play with those like a Lego. And then BPV is bit per value. So basically you say, okay, I have 8 bits that is shared between 32. So 8 divided by 32 is 0.25. So MXFP8 has 8.25 bits per element versus FP8 alone has only 8 bits. Make sense? Okay, I have to be careful here. I can not tell you everything, but I think 3 slides from here, I have a table that shows some numbers for AI2. AI2 is the AI engine for the AI engine built by AMD. It's targeting the AI applications and it's going to support a variation of data types. But usually, if you support FP8 or int8, it's very similar. If you want to support both, everything going to be double, right? Wider adders in int8, wider shifters in FP8. You put them together, everything going to be big, right? So it's data type alone, and also how many of them you're going to support in one device. The key point is that that's the generality part. Right? If you cannot just build one device that says, hey, just FP8, that's it, nothing else. That's good. That's a small and very nice implementation, but not too many people are going to use it. Yeah. And also, there are 2 ways to use these data types. If you want to use them for training, right, you have this intermediate format data type bfloat16 that you keep your activations in bfloat16. So if you do transpose, when you do the backward pass, there's no scale to be ruined. And from bfloat16, you can quantize your values into targeted data types and do your mathmul operations in those narrower data types. So faster, cheaper, and etc. If you don't want to do training, there is no point to keep track of the bfloat16. You can just get rid of the bfloat16 and forward pass, everything quantized, smaller memory footprint, and the same cheap mathmul operations. So I already made these points in previous slides, but I'm going to repeat them. Accuracy is not limited by precision. We can do much more in order to recover your precision when you quantize your models. There's a ton of redundancy in those models, so you can do a lot of compression. And there are like 3 categories. If you squint your eyes looking at those papers, you can separate them into 3 groups. Wider data types like FP16, bfloat16, MXFP8. You don't have to do much as a user. You can just direct cast your data types, your values into targeted data type like MXFP8, and see no change in your performance, like accuracy and the quality of your output. And it comes with some benefit for the computation gains. Like if you go from FP32 to MXFP8, you almost reduce your size by 4 times, right? If you go to FP16, it's 2 times. But for MXFP8, you need a compiler, you need a device that runs MXFP8, can compile MXFP8. PyTorch doesn't support scale data types, let alone MX data types. They're working on it. Hopefully soon they're going to support it. There are libraries out there that you can use in addition to like PyTorch, for example. We have Brevitas in AMD that you can use to quantize your models in PyTorch Playground. Use different algorithms in order to compress your models. But for wider data types, we don't have to do much. Direct cast, you're good to go. For the medium data types, like int8 FP8 and MX FP6, sometimes direct cast works, but if your input is complex, if the size of your model is small, if they can be a little challenging. But you can use usually post-training quantization methods that they adjust your weights a little. So when you quantize, it's not just like casting and rounding. There's a little more than that into it. But they work. They work. You can recover your the same quality as output running your model with these narrower data types. And then if you go to the extreme, like int4, MXFP4, there are data types even lower than that, like int2 and etc. But they didn't list everything here. You need to do a little more. You need to do some fine tuning, running a few epochs to adjust your weights. Perhaps you end up using some knowledge selection methods like teacher student model to recover the quality of your output. And if you do that, this is the table I was talking about. You can gain in computation, right? This is AI Engine 2. It's a custom processor by AMD that supports these data types. It doesn't have the MX data types yet. But if you just look at int8, right, multiplied by int8 versus int8 multiplied by int4, you can see that a number of mac operations doubles. And this is the mixed precision that I showed in that cartoonish drawing, like int8 multiplied by int4. Usually, wider data type is used for activations. Because for weights, you can just see them. They can modify them. You know the distribution and everything. But for activations, you just have some notion of the distribution. You don't know exact numbers. So you give a little more bits to activation. So if your activations are int8, your weights are int4, you can do 512 mac operations per clock cycle versus if it's int8, it's 256. And if you go wider, like int16, you end up at 64. So if you want to multiply 500, let's come up with an example. 256 activations, if you want to do the dot products on them, if they are on int8, you can do it in one clock cycle. But if they are in int16, you need 4 clock cycle. So latency right there. Also, you have to move all of those int16s into your processing unit versus if they are int8, the size is half. Yes. I want to say 1 gigahertz, but I think this guy is 1.2. I have to double check, but 1.2 sounds correct. Like int8 versus int16.
Yeah, they're reducing the number you can do, which makes sense.
Mm-hmm.
How is that hardware?
I probably cannot. I cannot. I don't know all the details to tell you, but you can reuse some of your logic in order to do 1 int16 or 2 int8. Yeah. All right. Let's look at some results here. These table, I'm going to show you a few tables, and there are from that white paper that I I talked about, we published it with Microsoft. This table is direct cast. Get your model, just cast your values to the target data type, and that's it, nothing else. There's no fine tuning, no post training, quantization algorithm running, nothing. It's just direct cast from FP32 to these data types. And you can see for MX int 8 and MX FP8, you don't lose that much. They're pretty close, right? And it's fine. Like for mobile net, which is pretty hard to quantize, going to MX int 8 even, you don't lose that much. But for MX FP8, because of resolution, you lose a little. If you go to MX FP4, it's horrible, right? Like 0.25. It's a lot of drop in your accuracy, right? So for these wider data types, usually they work pretty good. For the middle one, MX FP6, you lose a little, but it is still, maybe you can tolerate it. But MX FP4, you have to do something else. Now, you can use PTQ. This table, we generated this based on the method, we call it error diffusion. That method is not published yet. We are finalizing the paper, but it's based on a work from Brian Sabb's group. He's a professor at the mathematics department here at UCSD. He's a student, Jinji Zhang. He came up with that method to update your weights before quantizing it. So you try to reduce that delta that I showed you, that the weight is going to have a delta, you're going to produce some delta in your output. The goal is to reduce that fluctuation in the output by modifying the weights before quantizing them. And if you do that, you can recover a lot, right? These MXFP6 values are pretty much same as FP32. We didn't show FP8 or int 8 here because there was no point for it. It's good enough in direct cast. But for FP6, they're all pretty good, except mobile net, which is known to be hard for quantization. MXFP4, sometimes it's good. For mobile net, you cannot just recover it. But if I go back from 0.25, they came to 18.88. So it didn't reach the 100% recovery, but it had some improvement. If you want to recover the whole thing, you have to do some fine tuning. So fine tuning, it means you quantize, you go through a few epochs, you update again until you are satisfied with your results. NA here means there was no fine tuning necessary. The PTQ or direct cast was good enough. But you can see MXFP4 with fine tuning has recovered a lot. Even for mobile net, we are very close to 72. So 0.25 to almost 19 to 65. Direct cast, post-train quantization, fine tuning. And each of them, they have a cost. Direct cast, pretty much no cost. Fine tuning, you have to run a few algorithms to update your weights. Still cheaper than back propagation and running the epochs. Fine tuning, you have to pay the cost, but you can recover a lot of your accuracy. You also can use them for training. These GPT models this table was done by Microsoft. They did it in-house with their own data types, data sets. And between FP32 and a mixture between FP6 and FP4, that's the example I showed you at the beginning, that if you change the location of that cartoonish ellipse, sometimes you need to have mixed precision. So FP6 for activations, FP4 for weights, you can recover pretty much all of your records. So FP32 to here, that was your question probably, that can you recover it? Yes, you can. And this is for training. So training with these data types. Yeah. But it doesn't mean that you can do it for every application, every model, every time. I work for these. And I don't know if you listened to Microsoft keynotes yesterday. No. So these data types are already in Azure. Microsoft has its own processor Maya 100, and it supports the MX data types. OpenAI is using them, so they're real. They are actually being used. Probably, if you interact with one of those OpenAI products like GPTs, some of your data going to be run on these models. Not today, hopefully in the next few weeks. And I'm going to answer the question in a second. NVIDIA has its own H200. AMD is also pushing MI 300X, and both of them are going to be in Microsoft Azure. And so everybody is looking at these new data types. There might be changes in the future, but I can promise you no FP32 anymore. So if you want to train your models, consider those smaller data types. If you want to work on compilers, consider these data types. If you want to work on hardware architecture, consider these data types. Anywhere of this stack, if you are looking into data movement, packing the data, etc., you should consider these data types. These data types also going to end up on the CPUs as well. So don't limit yourself that I don't touch this device, then I shouldn't look. Okay, so there was a question here. Sorry, repeat your question. Yeah, okay. So to answer your question, I think it's better if I go back here. So for the training, the operations are done in those quantized data types, right? So the matmul is using the MX data type, but the output is in bfloat16 for training, because that block, when you transpose it, doesn't keep the orientation. So it was a mix, right? But if you do per tile quantization, yeah, you can use those, but we didn't try it. Did I answer your question? Okay, excellent. Let me go. Yes. If I do pre-training? Uh-huh. Yes, because oh yes. So the question is, if you do training with these data types, do you need the scaling? Yes. If you take the scaling out, right, the numbers you can encode in FP4 are just 16 numbers, and if you don't care about the sign, there are only 8 numbers. You don't have a lot of dynamic range and precision. So that scaling is very important. A bigger model? Yeah. There was like way before when I was working with Ryan, I looked into sparking neural networks, and they do binary stuff, like 1 bit, right? You can increase the number of parameters instead of doing FP32 or 4 bits or whatever number of bits. Have a ton of 1 bit operations. But how big that's going to be, I don't know. It's not something that people take it seriously. The size going to be very, very large. Yeah, but yeah. Okay, you have 5 more minutes, and I'm at the end of the slide. So these data types that going to be suitable for AI, sorry. They're everywhere. In PyTorch, you have to emulate them. Even if you want to do training, if your hardware supports those data type, you're gonna just run faster. data movement in your GPU, storage in the GPU, and number of calculations you do in the GPU or CPU or any other custom hardware, it matters, even in PyTorch world. When you export it to something like Onyx, the export format, how you encode them, how you transfer that information into your compiler. And also the compiler, what kind of optimization are you going to do that? Are you going to do there? How are you going to support the data movement between your different layers of memory? And how are you going to support like data flow or pipelining and etc. And also the device. I didn't cover these two parts right on the right side, but the good news is tomorrow we have a talk and my colleagues, Christopher and Steve, they're gonna talk about the open source compilers we have, MLIR AIE, that you can use to program those AI engines. And those AI engines are out there. You can buy a laptop with AI engine for around $1,000. There are small form factor boxes that they also have the AI engine around 700. And if you wait a little, the price is going to go down. But they're going to talk about the open source compiler. They're going to talk about the AI engine and Instinct GPU. Instinct GPU is the family that MI300X is from. And they're also going to do a demo on the box. So you can see the model in action running on AIE with smaller data types. And you can also get familiar with MLR AIE. And they are also enthusiastic, same as me, to work with you. So if you think you have a vague idea, contact me. If you have a good idea, contact me. If you have no idea, contact me. And that's my email, arizak@amd.com. Just memorize the first part. amd.com is obvious. And we have a couple of more minutes for questions. Yes. The direct cast? Good question. Yes. So why MXFP4 is 0.25, but if you look at like those ResNets, it's much better, right? So what is so significant about MobileNet? You know, what's the difference? They both classify ImageNet, right? One task. MobileNet is for mobiles, and it's much more complex. It's well trained. It's smaller, meaning the local optima that they find for that MobileNet is in a sharper valley, right? Versus for Resident 18 or Resident 50, it's wider. You have more room to wiggle. By wiggle, I mean when you quantize your parameter, is going to change their value to something else, one of those buckets that you have available in your target data type. So if your local optima is in a very, very sharp valley, right? You quantize them, you immediately lose a lot, immediately. But if they are wider, you have more room to change the values. So you can see in Resident 18, Resident 50, your MXFP6, it's pretty good. Actually, there is an example somewhere here that when you quantize, let me find it. When you quantize, you get some sort of improvement. That's the quantization noise actually works in your benefit. This guy? Yeah, yeah. Okay, yeah, MXFP6 versus MXFP8, you have more bits, but you get some improvement. That's because that model is large, your task is not that challenging, and also the quantization noise by log is working your advantage. Any other questions? So you mean like mixed precision? Yes, there's absolutely benefits in mixed precision. There are a number of papers. One of them is it has a very cool title. Are all layers equal? Because someone just randomly start quantizing different layers in ResNet, and for some layers it doesn't matter. You can just quantize them all the way to like int4. Nothing significant going to happen, right? So yes, based on your model and input, some of those layers you can just go very heavy on them. Like for example, for LLMs, when you have the KV cache, it's like K, Q, V, right? There are like three inputs coming to your self-attention. And when you talk, when you interact with the model, that KV value, the output, is saved and is being used for the next token. That's a cache. You can quantize that cache a lot in different ways. You can actually quantize the tokens. Like if I say, I like an apple, you just need to save like an apple, an I. You can get rid of the an, right? That's quantizing the tokens. You can also quantize those informations to be a little, fuzzy and vague by smaller data types. And you have to store it somewhere, right? You can reduce your data movement. Another example are, you actually know the Taylor, right? We remove the skip connections on ResNet, right? You can also quantize them very heavily, right? If you don't want to just remove them. Or UNet, you have those very, very long crop and copy connections at the very top of UNet, right? You produce the output, and the lifetime of this output is super long. You have to just keep it, go through the U of the UNet, at the end use it. Where do you want to keep it? Off chip, on chip, level 1, level 2. If you quantize it, you probably can just keep it next to your processor in L0 or L1. Not L0, L1. So yes, you can quantize different parts, but finding like which one, that's the million-dollar question. Yeah, if you have it, let me know. All right. We ran 3 minutes. Yes. Yeah. So for now, pretty much everybody, huh? Yes, the question is the hardware that is built for these MX data types, are they all going to support the same data types? For now, everybody pretty much agreed to support these. Yeah. Yes. Here, Microsoft has the library on GitHub. It's Python, but you can play around with them, so you can emulate them. And hopefully soon we're gonna support, or we're gonna put our open source library on um, uh, on on AMD GitHub. What do you mean by for the hardware? Oh, you mean the custom kernels? We don't have them open source yet, but for CPU and GPU, there are some that pretty much I assume everybody other than AMD have, but I don't think they're open source to public yet by anybody. Yeah. Yes. Um, Again, it really depends on what you want to do. OpenAI, in their dev day, they announced this new product, GPTs, right? You start with GPT, you do something specific with it, like come up with best recipes for fruitcake, right? And then you put it in the market, someone else is going to come and use that customized GPT, right? For the base model, it's better to keep it in high bit resolution. But if you make a product a model that is for a specific task, it's easier to quantize it. If you quantize the base model, it's very hard to make it generalize and support different applications. Does it make sense? Kinda. Okay, right. For example, that I'm going to go back to that absurd data type on data set on. It's not absurd. It's very, very easy. Like MNIST of LLM. It's like classifying tweets. Is it hate speech or not? Two classes, right? If you have a base model, you want to quantize it for that data set, right? Easy peasy. But if you quantize the base model, then you cannot use it for multiple applications. That's what I'm trying to say. All right. Good. All right. Thank you.